Hello and welcome to the alpha-amylase experiment. We are going to test the alpha-amylase enzyme and its ability and rate at which it catalyzes the hydrolysis of starch to make glucose and/or maltose equivalents. So looking at the alpha-amylase, in our body we actually produce alpha-amylase in our mouth and use that to start breaking down starches before those starches actually enter into our stomach. So on this image here we have a representation of starch where we have several alpha-1,4 glycosidic linkages. So essentially all of this straight line down here and the line within this set of glucose molecules are all 1,4 glycosidic linkages. So looking at the actual sugar structure here, the oxygens on here aren't represented all that great. So the oxygen's actually within the ring here. So I'll show you a better representation in just a second. But this does show the alpha linkages because on this anomeric carbon right here, the oxygen is down or on the opposite side of this CH2OH, and that is linking to carbon number 4 of the next glucose molecule. So on our glucose molecule, starting from the first carbon, which is the anomeric carbon, we have carbon number 1, carbon number 2, carbon number 3, and carbon number 4. So in this blown up image here, we're highlighting the alpha-1,4, so carbon number 1 on this glucose equivalent and carbon number 4 on this glucose equivalent, as well as our alpha-1,6 linkage. So on this molecule right here, which is this one right here, we have carbon number 1, and that's connected to an oxygen, which links the next sugar, and that carbon right there is carbon number 6 on the next sugar. So that's our alpha-1,6 linkage. All right, let's look at the molecule in a little bit more detail with a slightly better structure. So this right here is another representation of a starch polymer. So in this case, we have our linkages on carbon number 1 and carbon number 4, and specifically looking at this carbon here. So looking at this carbon right here, this is an alpha carbon. Our oxygen is on the opposite side of our CH2OH, and it's linking from its 1 position to the 4 position of the next glucose molecule, which, based on the brackets here of our polymer, would be this bond right here, which is connected to an oxygen, which links carbon number 4 of the next. So this is another representation of that polymer. So let's look at glucose in a little bit more detail. So in the biochem class, you guys have seen Fischer projections and Haworth projections of glucose. So let's look at that in a little bit more detail so we have a better understanding of what these two represent. So the Fischer projection of glucose is the open ring form. So this is in the open ring form. It's actually not a ring structure. So for the Fischer projection, I've numbered the carbons on here. So carbon number 1 is our carbonyl carbon. Carbon number 2, 3, 4, 5, and 6, all the way down this carbon chain. So we've got carbon number 1, 2, 3, 4, 5, and 6. So that's the Fischer projection of glucose. If this ring closes, we have the chair structure, and we have a Haworth representation of glucose. Specifically, I've drawn the alpha version of glucose. So this is alpha-D-glucopyranose for its formal name. Thinking about the mechanism for this, what happens is the alcohol attached to carbon number 5, so this alcohol is going to attack and form a bond with carbon number 1. It'll push these electrons up, and eventually with a couple proton transfers we will deprotonate this, protonate that. This will then be an alcohol functional group. So that oxygen right there, like I said, on our Haworth projection will be an alcohol functional group. So on carbon number 1, down here, we have an alcohol functional group. So let's take a second and go ahead and just number all the carbons on this chain to see if it matches up with the chain that we have above. So looking at, let me just unselect everything real quick. So we've got carbon number 1 through 6. So carbon number 6 is the CH2OH. So that is this carbon right here. Carbon number 5 is the carbon that CH2OH is connected to, which is that carbon there. And that is then connected to carbon number 4, not directly connected to an oxygen yet in our Fischer projection, but we know that that oxygen will eventually be connected to carbon number 1 once we do that nucleophilic attack. So carbon number 5 is connected to an oxygen which is connected to a carbon. So there's the oxygen, there's the carbon, but this carbon here is that carbon there, so that would be carbon number 1. So going back the other way then, we have carbon number 4 here, which is carbon number 4. And then connected to 4, we have 3. And connected to 3, we have 2. And connected to carbon number 2 is carbon number 1. So this right here is carbon number 1. It'd be great to practice the mechanism. If you do it under acid catalyzed conditions, you'd protonate the aldehyde first, so you'd protonate that oxygen. Then do a nucleophilic attack where this oxygen binds to that carbon, the carbonyl carbon of the aldehyde functional group. You would then push these electrons up to the oxygen, making that an alcohol, and then the last step you deprotonate this, and this oxygen is this oxygen here. So if that had a hydrogen attached to it after it did form that bond with carbon number 1, you would then deprotonate that to give your final product. All right, so there is the Fischer projection and the Haworth projection of glucose. Now, glucose and maltose share some characteristics. One is that they are both reducing sugars. So they are reducing sugars because they have the potential to reduce something which can be reduced, which means that glucose and maltose would both be oxidized. And so looking at the Fischer projection of glucose, this aldehyde functional group right here, so this aldehyde functional group can be oxidized to form a carboxylic acid. If we oxidize this, something else has to be reduced. In this experiment, we're using 3,5-dinitrosalicylic acid, and our 3,5-dinitrosalicylic acid is going to be reduced, specifically the nitrate group, the NO2 group on carbon number 1, 2, 3, on carbon number 3 is going to be reduced to form NH2. Now I drew maltose on here. This is a very similar structure. One of our anomeric carbons has the potential to be oxidized and the other does not. So looking at our two anomeric carbons we have, so the oxygen-carbon is the anomeric carbon. On that here, this does not have the potential to be reduced. We can't open this ring up here because we don't have an alcohol functional group here. However, on our other anomeric carbon, so our oxygen, carbon, oxygen, that carbon is an anomeric carbon. We have an alcohol here. This can open up, very similar to what we talked about here, to form a free aldehyde functional group where now this carbon-oxygen bond right here would then have the double bond. That would be our aldehyde functional group. So this ring could open. We could then have an ability to oxidize this, which could reduce something else like dinitrosalicylic acid. All right, moving on to the last step, let's look at the reaction, specifically the oxidation-reduction reaction between maltose and 3,5-dinitrosalicylic acid. So if we were to oxidize our maltose sugar, I'm just going to copy that here. So we're going to form a product here, and this is going to be no longer maltose when we form it. Also, we have to open that ring before this reaction happens. So this bond has to break. That conveniently became an alcohol functional group. To actually break that bond, though, we actually had to do a couple proton transfers and then form an aldehyde functional group. So that actually, this carbon-oxygen bond right there is our aldehyde functional group. And I'm going to actually move this alcohol over a little bit so you can see that a little bit more clearly. And then finally, I'll just make this wedge a straight line, and really I'll just make all these. So the reason these are bolded is so you can visualize that the chair is in a flat conformation, so that's like coming out of the screen towards you. Use the image size of this so I can fit it with all in a straight line, but this is the structure right now. So we've actually opened up our ring to make our aldehyde functional group. But what I haven't shown is the fact that this was actually oxidized. So it has not yet been oxidized based on what I've drawn. So if we're going to oxidize this, we actually have to oxidize this carbon further than it is. So in order to oxidize this, we'll convert our aldehyde functional group into a carboxylic acid functional group. So now, instead of this carbon taking all the electrons when it's battling the original hydrogen that was there, now that oxygen takes all of them. So we have further oxidized this carbonyl carbon. We converted it from a aldehyde functional group to a carboxylic acid functional group. Our dinitrosalicylic acid is what was reduced. So for our dinitrosalicylic acid, our nitrogens for both of our nitrate groups were fully oxidized. We're going to reduce one of them and reduce it to be an NH2 instead of an NO2. So now our dinitrosalicylic acid is no longer dinitrosalicylic acid. We actually have an amine at the 3 position. That nitrate was fully reduced to an amine, where our aldehyde was fully oxidized to a carboxylic acid. So that is the oxidation reduction reaction that occurred. One more time, maltose was oxidized, dinitrosalicylic acid was reduced. All right, looking at the next, we have sucrose here. So in the experiment, we are actually going to be using starch, which does not have a free OH group on its anomeric carbon. Sucrose is actually the same way. We also do not have a free OH group on our anomeric carbon. Even though it's not a long chain polymer, we still don't have that OH group on our anomeric carbon. So looking at the 2 components of sucrose, our glucose molecule here, this anomeric carbon is bonded to an oxygen, but that oxygen is bonded to something else, so that's not a free OH group on our anomeric carbon. For fructose, our anomeric carbon is here, and that is connected to an oxygen, but that oxygen is connected to something else. It's not an alcohol functional group, so we also do not have a free OH group there. So sucrose is not a reducing sugar for the same reason that our starch polymer is not a reducing sugar. So our anomeric carbons do not have a free alcohol functional group attached to them. So we can't do an oxidation reduction reaction with dinitrosalicylic acid when sucrose is in this state. And so for this, there is no mechanism to show. This is simply no reaction. All right, for setting up the experiment, we're asked to make a standard curve of maltose from a 15 micromole per milliliter stock solution. So we need to make a standard curve of 0 to 5 micromole per milliliter concentrations from a stock solution of 15 micromoles per milliliter. So I've went ahead and set up my C1V1 equals C2V2 equation. So I'm going to make my C1 the stock concentration, which is 15 micromoles per milliliter. And we're going to have that for concentrations all the way up to our 5 micromoles per milliliter. I'll extend that one more time. And our final volume for all of them for our 0 to 5 micromole per milliliter concentration is going to be 1,000 microliters or 1 milliliter. So now we need to calculate the volume of stock solution necessary to make this. So solving for V1, I'm going to take C2 times V2 divided by C1. So I'm going to say equals, and that's going to be C2 times V2 divided by, this is the same thing every time, but I'll just do C1 anyway. So divided by C1, So for the first, if we want a 0 micromole per milliliter stock concentration, it makes sense that we're going to add exactly 0 milliliters of our stock solution. So conveniently, when we do this in Excel, I can actually just drag this down and it'll auto-calculate everything for me. So in this case, for a 1 micromole per milliliter final concentration of stock solution, I need 66.66 repeated microliters of V1. This is in microliters because I made my V2 units in microliters. So if I drag this down, I would get then these numbers. That one's a little bit clean. The others seem like I don't really want to transfer that with my pipette. I could get it very close. I'd rather just have clean numbers. So for our, what we could do is basically use something where we can divide by 15 and get a whole number. So if we want to adjust these a little bit, I think we can do this and then I'll make the whole thing look a little bit cleaner. So instead of 1, we could just do 1.5. And then instead of 2, we just double 1.5 and just basically keep adding 1.5 all the way down the list. So 3 plus 1.5 is 4.5, and 4.5 plus 1.5 is 6. So with this, we've got 1, 2, 3, 4, 5 different things that we're testing. I think that's adequate. So that is going to be the amount of stock solution we need to make all of these. So for water to add, we might as well go ahead and calculate that for all of them. So we'll label these actually test tube 0, 1, 2, 3, 4. So we're going to have 5 total different concentrations. I'm just putting this as test tube 0 because it's our 0 concentration. So for water to add, we know that we need to add 0 microliters of stock solution, and our final volume is 1,000 microliters. So I'm going to say 1,000 minus our V1 value for all these. Oops, I forgot to be equals there. So equals 1,000 minus our V1 value for all those, and then we can drag that down. So that's the number of water that's the amount of water we need to add to each test tube, and then logically it makes sense that we need to add less water for our test tube with higher concentration. So this is the table that we need. This is essentially the set of test tubes that we need to make. So test tubes 0 through 4 need to have 0 to 400 microliters of stock solution depending on the test tube, and then 1,000 to 600 microliters of water depending on the test tube. So that's what we're going to set up in lab next. Right now I've got a P1000. I'm adjusting that to 1,000 microliters or 1 milliliters, and I'm going to put a pipette tip on that, and I need to get some distilled water from the water faucet there. That way we can go ahead and add our 1,000 microliters in test tube 0, and we'll slowly scale that down by 100. So we're going to add 900 microliters to test tube 1. And you can see a little water bubble come up in my pipette tip there, which is why I've pushed that back out. So it's important to uptake it very, very slow into that pipette tip so you can get an accurate volume. And I cut out a little bit there of filling the last couple test tubes. Here I'm about to fill the 5th. I'm actually just counting here to make sure that I should be filling 5 because I had 6 on the rack because I originally planned on 6 before I redid my calculations. So I took the last test tube out and I have 5 test tubes now where I need to add the appropriate volume of the maltose stock solution to each one. And for the last test tube that needs the maltose added to it, I'm adding 100 microliters. So that would be test tube 1, and then test tube 0, I'm not adding anything to because I already added 1,000 microliters of water, and that's just my water solution. And now I'm getting out a little bit of color reagent, so I can add 1 milliliter of color reagent to each test tube. I added a little bit much here if this was a one-day experiment, but I'm actually going to do all sets of it, so I need enough for part 2 as well.
Good.
And again, this is 1 milliliter or 1,000 microliters of color reagent to each test tube. And you can see back there the hot water bath is already on and the water is boiling very lightly. So I'm going to put these in the hot water bath for exactly 5 minutes. And next, to prepare for the analysis of each of our samples, I'm adding 8 milliliters of water. To 5 additional test tubes. That way when I take my samples off the hot plate, I can add all those in very quickly to stop at 5 minutes. So this is the last test tube. That has 8 milliliters of water.
Okay.
And now that they've been in the hot water bath for 5 minutes, we're taking them off and adding the 8 milliliters of water to each test tube. And you can actually see the difference in color between the more concentrated samples. So of the 2 milliliters that was in there, it obviously gets lighter to darker. It just basically lightens up all of the colors a little bit more once we add in our water. And you can see the importance there of measuring the 8 milliliters of water with a graduated cylinder for each one. And that third test tube is a little bit wider than the other, so it looks like the volume level is a little bit lower, but it is actually the same volume level of water. Okay, now we've moved over to the Genesis Spec 20. I've got some distilled water that I'm adding to the small cuvette. I'm going to put it in there. So the actual wavelength flows front to back in that machine. So there are basically two like tinted or shaded sides of that cuvette, and then 2 are clear. You want to make sure that the wavelengths are flowing through the clear side, so front to back. I zeroed that, so I put water in there and zeroed that to account for any absorbance within water or that actual cuvette, so essentially we're canceling that out. And now we're going to add half of our sample and measure the absorbance for our 0 microgram per milliliter concentration of maltose. I'm going to enter these values straight into Excel. and I'll go over that in detail once I graph the values for our standard curve. See there, I'm dumping all those into that beaker, and then I'll rinse them in the sink to measure that, to make sure that glass is thoroughly rinsed. I didn't dry it thoroughly each time. I actually didn't dry it thoroughly after I ran my water sample through there. So there's a small amount of residual water for each one. That's kind of why I didn't dry it after I ran that water sample, so that it wasn't biased, making that first one more concentrated. And here I'm just drying the outside of the cuvette to make sure there's no water on there, because that will impact the absorbance that equipment reads. Also, I'm not actually using the computer connected to that. I'm not using the program that's synced with the Genesis 20. I'm actually just entering the data that I can read on that screen straight into Excel. For these last couple samples right here, I'm just going to go ahead and show you the data I got for the standard curve of this. This is very similar to what we did for the Biuret assay. So if you need to review how we made that graph, I was very detailed in Excel about that. Make sure that you have your concentration of maltose as your x-axis. So you want your x-axis to be in the range of 0 to 6 micromoles per milliliter, and then your absorbance values are going to be on your y-axis. You're going to enter all those absorbances and make sure you combine that data set when you fit that with the linear standard curve. So make sure you also show the y equals mx plus b equation, as well as your r squared value on that graph when you present it for this lab report. Should I spin this one more time?
I think we're good.
Right, for this next part of the experiment, we are preparing different dilutions of my spit. So I spit in that test tube, and from the water of the spit, I'm adding 2 milliliters into a test tube and 18 milliliters of water. So right now I'm getting 18 milliliters of water. It's referred to as a 1 to 10 dilution. So it is 1 part of the reagent and 10 parts total. So if we divide those both by 2, it's 1 to 9. So 1 part of the reagent is 1 milliliter of my spit. Add 9 milliliters of water to that, you have 10 total, so that's the 10 parts total in the 1 to 10 dilution. For the 1 to 100 dilution, we're going to take a milliliter of the 1 to 10 dilution that was made, put that in another test tube, and dilute that with 9 milliliters of water. So we're taking 1 part 1 to 10 dilution, diluting that with 9 milliliters of water, otherwise known as diluting that tenfold, to make our 1 to 100 dilution. After we make that 1 to 100 dilution, we're going to make sure we stir that really well, and then we're going to take a milliliter from that. So that needs to be thoroughly stirred to make sure that some of my saliva is definitely coming with that to make the 1 to 1000 dilution. So essentially we're going to dilute that tenfold again to make the 1 to 1000 dilution. So right now I'm getting 9 milliliters of water in that graduated cylinder. At this point, I'm adding a half milliliter of my diluted saliva to each test tube. So the first test tube has my 1 to 10 dilution, a half milliliter. The second test tube, so I've got 2 rows. I'm just doubling the experiment. So the front row and the back row have the same thing in both. So that is adding to the front row, and this is adding to the back row. I have 0.5 milliliters of my saliva in that, and that's the 1 to 100 dilution. And then lastly, I'm adding the 1 to 1000 dilution. That'll be the third test tube. And in the last test tube, that's my control. I'm just adding a phosphate buffer with nothing in it, so mostly water. And now to be careful with the time, so these can sit for 3 minutes at room temperature. I'm going to go ahead and start my timer before I add the starch solution. So that what I'm adding right now is starch solution that is dissolved in buffer solution. And I'm going about every 5 seconds, adding first to my 1 to 10 dilution, now to the 1 to 100 dilution, and now to the 1 to 1000 dilution, and then finally to the controls. And this is going to sit for exactly 3 minutes. So right now in the experiment, what's happening is my saliva is working hard, specifically the alpha-Amylase in my saliva is doing everything it can to break down that starch into maltose equivalent, maltose or glucose equivalent. So essentially the more of that starch polymer that's broken, the more potential there is for the sugars that I'm making to reduce the color reagent, that dinitrosalicylic acid. And after 3 minutes, I'm just getting ready to add the color reagent. So I'm adding 1 milliliter of color reagent to each test tube. And I also have the hot water boiling so that once I add those, the 1 milliliter of color reagent, I can go ahead and put those in the hot water bath. These have been in the water bath for almost 5 minutes. I'm just about ready to take those out. And you can see the color difference there. So the specifically the two on the right, the control and the 1:1000 dilution look remarkably similar. It looks like pretty much nothing happened from the start. The ones on the left, though, look like definitely something's happening in there. So specifically, we had some sugars like maltose and or glucose in solution that could react with that color reagent. So that means some of the starch was actually broken down by my saliva. Now we just need to figure out exactly how much based on those two dilutions. We're going to dilute these with 8 milliliters of water. I'm going to go ahead and speed through that. And we skipped a couple there. I'm ready to put 8 milliliters in the last test tube, which is the second control. And now we're ready to switch over to assess the absorbance of each of them. So I'm doing the most concentrated ones first.
I don't recommend using that one again.
And again, the absorbance shows up on the instrument, so I'm just entering that value into the computer right now. And you've probably seen this enough times, so each time I'm going to thoroughly rinse the cuvette. It was still wet for the first one. So I'm going to test each one twice, and then finally test the control. I'm going to go ahead and show you the data that I got, so you guys will need to write this down and present this for your lab report. So for the control, our absorbances were slightly higher than the 0 amount of maltose for our original table that we made. For the 1 to 10 dilution, we had a significant absorption, and for the 1 to 100 and 1 to 1000, we had little to no absorption related to that. So essentially, my samples were too dilute past 1 to 10. Here's the original table that we got for part 1 of the experiment. So note that the concentration of maltose being at 0 had an absorbance of 0.036 and 0.039. We essentially need to subtract that out when we adjust for our controls that we're doing in this experiment. So that's what I have on this next chart here. So for the control, which was starch with no enzyme present, it was a little bit higher than we got for our 0 micromole per milliliter of maltose concentration. So we essentially need to average those two values, our two control values, and then subtract the control for our 0 maltose concentration from the control for our starch with no enzyme present. Once we have that, we can follow the rest of the calculations, and I'll expand that here in just a minute so you can see more clearly. So again, take another glance at those test tubes. It's obvious that we got little to no activity for the controls, as well as our 1 to 100 and 1 to 1000 dilutions. So here is a larger view of the table that we were looking at earlier, essentially subtracting out basically subtracting our 0 micromole per milliliter maltose concentration from our control. So when you look at taking these calculations a little bit further, when you convert your absorbance per minute, you need to take the absorbance of your saliva minus the control divided by 3 minutes. So for the control, I'm actually going to use the difference between our two controls, which means that we're going to take our absorbance, our average from our 1 to 10 dilution, and subtract out the average between our two controls. We're going to divide that by 3 to get us our value of absorbance per minute. All right, as we continue, we're going to prep for the effect of temperature on an enzyme activity experiment. So we're just going to go forward with the 1 to 10 dilution that we have and set up for the different temperature baths. As I set that up, let's talk a little bit more about the effect of concentration on enzyme activity. So what we saw is for the 1 to 10 dilution, we definitely had some enzyme activity. So the alpha-Amylase was undoubtedly breaking down that starch, making glucose or maltose equivalents, which is why we had the large absorbance for the 1 to 10 dilution. When we diluted it past 1 to 10, so for the 1 to 100 dilution and the 1 to 1000 dilution, we had pretty much no enzyme activity. It was essentially too dilute for anything relevant to happen. We were unable to break down that starch hardly at all. So right now we're setting up for, again, effective temperature on enzyme activity. So we are putting 0.5 milliliter of enzyme and 0.5 milliliter of substrate in the first set of test tubes, so in the front row, and in the back row we're putting 0.5 milliliters of substrate and 0.5 milliliters of phosphate buffer in the back row. So essentially there's no saliva, no enzyme for our control in the back. And hopefully we agree at this point that substrate means starch. So we actually have starch in solution, and we have starch in both our control as well as our experimental set of test tubes, which has also our enzyme in it. So right now I'm adding more of the my diluted saliva to these front test tubes here. And we're putting these in the hot water bath, so the temperature ranges from 25 to 60 degrees Celsius. You can see I'm putting it in the 45 degrees Celsius and the 60 degrees Celsius hot water bath right now. Both the controls and the standards were in there. We had those in the hot water bath for exactly 3 minutes. We then took them out of the hot water bath, and we're going to stop that alpha-Amylase catalyzed hydrolysis reaction by adding 1 milliliter of color reagent to each of those test tubes. So you can see on the P1000, I'm adjusting it to 1000 microliters and adding 1 microliter to each test tube. So you can see actually for that first one, it looks like the controls and our reactions with enzyme look fairly similar in color. Which makes sense because we essentially haven't incubated these for the reaction to happen yet. So hopefully within the hot water bath we're going to see some differentiation between the test tubes, and my guess is that at 37 degrees Celsius, which is approximately body temperature, my guess is that we're going to get a little bit more reactivity from my alpha-Amylase breaking down a little bit more of that sugar.
See how much darker it is?
So now you can see differentiation within those test tubes. Definitely the controls are not nearly as dark as the experimental ones. And for the experimental ones, you can't really see the range because I don't have them in order yet. But definitely something is happening for our test tubes. So after those, we're in the hot water bath for exactly 5 minutes. Taking those out with the controls. Here's a pretty good view. You can see that that first test tube to the left is a little bit light, and the last test tube to the right is also a little bit light. The three in the middle are all about equally as dark. So we've got definitely quite a bit of darkness for the three middle test tubes, and it's a little bit lighter on the two outside test tubes. And that'll be a little bit more clear after these are diluted. So right now we are adding 8 milliliters of distilled water to each of the test tubes. So I skipped ahead a little bit, so we're to the last two. Let's go ahead and dilute those before we test on the Genesis Spec 20. And for testing, again, we're testing each temperature with both the control as well as the sample that actually had the alpha-amylase enzyme in the solution.
The back's just all standard again, right?
Yeah.
Alright, at this point, you're welcome to continue to watch me to fill the cuvette and run each sample as well as the control, but here is the data from the experiment. So for the room temperature experiments, it looks like we do have some alpha-amylase absorbance. It's not quite as high though. It looks like it actually keeps increasing up to 45 degrees. So that's actually slightly surprising. So I would have expected, again, 37 degrees for sure to be the highest. It definitely was higher than 30 degrees, definitely higher than 25. But 45 degrees actually seemed to be the optimal temperature based on the numbers that we looked at. So it's hard to say if a little bit more or a little bit less than 45 was optimal. Based on the sharp drop-off at 60, I'm going to guess a little bit less than 45 was probably optimal. So a little bit warmer than the mouth is actually the optimal temperature that alpha-amylase seems to function based on this specific experiment. Again, I would have guessed probably a peak at 37. It's just going to be offset to 45 in this case. For this table, we have the alpha-amylase absorbance and we have the control absorbance. When you adjust for this, adjusting for the control, you need to take the alpha-amylase absorbance minus the control absorbance from this experiment, and then from that control absorbance, you need to subtract out the 0 milligram per milliliter maltose concentration absorbance. So you're going to take, again, the alpha-amylase absorbance, subtract out a very small number to get your absorbance, and that is based on a rate per 3 minutes. So you need to go ahead and divide this by 3 to adjust that to a rate per minute, and then you can convert that absorbance into maltose concentration using your graph from the earlier part of the experiment. Once you have that value, you can then convert maltose to enzyme activity rate, which is what we want for our final data. So as we continue, let's talk a little bit more about the reason why the absorbance of alpha-amylase was so low at 60 degrees. So once you get past, obviously, well past 45 degrees, you reach a point where you have enzyme denaturation. So essentially the proteins start to unfold, so you deactivate the enzyme. And then with colder temperatures, it's just simply the activity, the rate of reaction is just a lot slower if it's much colder. And again, it makes sense that 37, which is the body temperature, the temperature inside your mouth, is going to be the optimal reactivity conditions for alpha-amylase.
All done? Perfect. Good.
For this part of the experiment, we're measuring the effect of pH on enzyme activity. So I'm adding phosphate buffer with no starch in it to my control test tubes in the back. And next I'm going to add the starch solution at varying pHs to both the front test tube as well as the control. And I jumped ahead a little bit, so now we're adding our pH 10 phosphate buffer to the last test tubes. And now we're going to add the 1 to 10 enzyme solution to each of the experimental test tubes. And now these test tubes are going to incubate for exactly 3 minutes. And after incubating at room temperature for exactly 3 minutes, we are adding the color reagent. Do each of our solutions as well as the control. And soon we'll put those on the hot water bath. And similar to the temperature test, it's good to start thinking about what you think what conditions would probably be ideal for this reaction.
Water again? Okay, now go.
So we're putting those on the hot water bath. Those will sit on the hot water bath for exactly 5 minutes. And thinking of the pH again, so the pH in your mouth is actually close to about 6.9. The pH in your stomach is a lot lower, so that's definitely acidic. But for alpha-Amylase to function, it actually needs to be at a much more mild pH, which again,
Okay,
about 6.9. So we expect to see a similar range of conditions for this experiment, where again, if we're at a very low or a very high pH, I don't expect the alpha-Amylase to be able to function at optimal capacity, but I think for the mid-range, I definitely expect to see the alpha-Amylase be reactive. And it looks like that is what we're seeing there. We need to dilute these with water to give a better idea of what we're referencing, but it looks like for our pH 4 and pH 10, there's very little reactivity there. For our mid-range ones, so pH 6, 6.9, and 8, it looks like we definitely had some activity. Now after diluting that first one, it looks like it was actually relatively low. Even the second looks kind of low. But we'll have a better idea once we take the absorbance of each of these samples. And to finish up the experiment, we're taking the absorbance of our samples where we have our saliva with starch at a pH range of 4 through 10, and then also taking the control where we have starch and buffer with no saliva. And again, we're going to take our absorbance that we read here, take the control absorbance that we get from this, subtract out the absorbance of our 0 milligram per milliliter maltose absorbance to get us our number. What you guys need to do is finish the calculations on this table based on the math that I just discussed. Don't forget to divide that number by 3 before you convert that absorbance to maltose concentration using your graph. And then convert absorbance maltose to concentration maltose using the graph. Once you have that maltose concentration, using the y equals mx plus b equation, you need to then convert maltose to enzyme activity in units of micromoles per maltose per milliliter times minute, and that needs to be corrected so that we are assessing our undiluted maltose. So I think you guys have seen the Genesis Spec 20 plenty from here, and that is all of the data you need for the experiment. Again, this is 2 sets of experiments combined, so experiment 6 and experiment 7 have been combined into one. there is one lab report due for the set of experiments. So essentially think of it as all as one experiment, and there is one lab report due for this experiment. And the guidelines for the lab report will be posted, and that link will be available on Canvas. I'll keep working in the lab for a little bit longer just to double check some of this data, and I look forward to seeing you guys back in the lab as soon as possible.